All right, so for light in the electromagnetic spectrum, what evidence is there that light is a wave? It diffracts. Only waves diffract. Light will bend through a medium. So that's how we know it's a wave. We call light, it's not a mechanical wave, it's an electromagnetic wave. Or an EM wave. What evidence can you cite to support that light travels through a vacuum? Light from the sun travels, do not know how to spell travels, through space to the earth. Space is a vacuum. There's nothing there. There's no medium to hold a sound wave to travel through space, but a light wave can travel through space. We see that because the sun shines on us. What is the velocity of an electromagnetic wave in a vacuum? This is the speed of light. We call it c because we use it so much, because it's a constant. And it's sort of this constant that defines everything else, because this constant never changes no matter how fast you're moving. Light always travels at 3 times 10 to the 8th meters per second in a vacuum. Why do you think the light is less in the atmosphere than in the vacuum? Okay, because of this. Light moves through the objects, and so the more stuff you put in light's way, the more and more it slows it down. On a molecular level, what you see is an atom absorbing and then retransmitting that light, and that takes a little bit of time. Not a lot, but a little bit. What range of wavelengths are visible to humans? We have 400 to 700 nanometers. Sorry, that's the wrong N. Nanometers are visible to a human, so that's 400 times 10 to the negative 9th to 700 times 10 to the negative 9th meters. It's a very small bit of the entire electromagnetic spectrum. How the frequencies of infrared, visible, and ultraviolet light compare? Okay, so the frequency of infrared light is less than the frequency for visible light, is less than the frequency for UV light. List the colors in order of lowest frequency to highest frequency. That was going to be exciting, but I don't have all the colors. So what you have is red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. And it turns out that the violet is the most energetic. What affects the energy of an electromagnetic wave? The frequency. And this is what's different about the electromagnetic wave. This is what's different about light than something like sound. In a sound wave, the amplitude affects the energy. In a light wave, the frequency affects the energy. Sorry, the frequency affects, the energy. What types of electromagnetic waves are most penetrating? Low energy. So like radio waves. Those can pass through things without making any effect on them at all. They penetrate straight through with no big deal. Visible light stops at your hand. A radio wave will go through it. No big deal. You can't really slow it down that much. The longer the frequency, the easier it is to transmit through something. Radio waves, the those are the lowest energy that we have, can pass straight through a planet, really, if the wavelength is big enough. The smaller the wavelength, the least penetrating it is. Draw and label the electromagnetic spectrum. Guess what? You just go look that up on the video. When white light is shined on a piece of blue cloth, what happens? So, when white light shines on blue cloth, blue light is reflected. All others are absorbed. That's what it means to be blue. It's reflecting blue. It's absorbing everything else. So when you put a black object in the sun, it is going to absorb everything else. When you put a white object in the sun, it reflects everything else. That's why black objects are really good at heating up in sunlight, and white objects aren't. They're reflecting the energy off. There are three primary colors of light: red, blue, and green. And this is primary colors of light. If you want to get into a discussion about this with your art teacher, when we do light, it's additive color. So the three colors of light when we add are red, blue, and green. When it's reductive, it's the other ones. Yellow, cyan, which is a bluish color, and magenta, which is a reddish color. So when we have red and blue light combined, we get cyan. Sorry, red and blue light is magenta. When red and green light are combined, we get yellow. When blue and green light are combined, we get cyan. When red, blue, and green light are combined, we get white. If you want to, you could get like a magnifying glass or something and look at your TV or your computer screen with the little bitty pixels. Now they're super small these days, so it would take a lot to be able to zoom in on them. But those little pixels, each single pixel is composed of a red, a blue, and a green dot. And how bright the red, blue, and green shine is what determines what color comes out of there. So for your TV screens, for the most normal ones, you get RBG, red, blue, green. Those three combinations can create most and all of the colors that you see. So there you go. An electromagnetic ray has a wavelength of 3 × 10⁻⁶ meters in a vacuum. And remember, for an electromagnetic wave, the speed is 3 × 10⁸ meters per second. What's the frequency of the wave? What's the period of the wave? Well, I know that V is equal to F lambda, so if I want the frequency, we got to divide by the wavelength. So the frequency is the velocity divided by the wavelength. So 3 × 10⁸ meters per second divided by the wavelength of 3 × 10⁻⁶ meters gives me, and because this is scientific notation, we're back here, that gives me 3 second E8 divided by 3 second E⁻⁶. That gives me 1 × 10⁻⁴ hertz. So 1 × 10⁻⁴ hertz. Then the period is 1 over the frequency. So 1 over 1 × 10⁻⁴ is equal to 1 × 10⁻⁴ seconds. Not a lot of time in between there.